Hi everyone. So in today's video, we are going to go over this paper called TorchTitan, One-Stop PyTorch Native Solution for Production-Ready LLM Pre-Training. This is by folks at Meta and Harvard University. So first things first, I haven't read this paper yet, but I've looked at the TorchTitan library a few times to get inspiration and to see how they implement certain things. And this paper is supposed to be uh, have like the insights behind the library. All right. So without further ado, let's delve right into it. The development of LLMs has been instrumental in advancing SOTA NLP applications. Training LLMs with billions of parameters and trillions of tokens requires sophisticated distributed systems that enable composing and comparing several SOTA techniques in order to efficiently scale across thousands of accelerators. Yep, so far, so good. However, existing solutions are complex, scattered across multiple libraries and repositories, lack interoperability, and are cumbersome to maintain. I totally agree. Uh, like, for instance, even if you look at, say, NeoX, which is a very good library to pre train LLMs, you'll see that one of the things that they do really good is to bring together things from different libraries like Transformer Engine and then stuff from Megatron and have their own custom stuff in some places and so on. So thus curating and empirically comparing training recipes requires non-trivial engineering effort. Yeah. This paper introduces TorchTitan, an open source PyTorch native distributed training system that unifies and advances SOTA techniques, streamlining integration and reducing engineering overhead. TorchTitan enables seamless application of 3D parallelism in a modular and composable way, while featuring elastic scaling to adapt to changing computational requirements. The system provides comprehensive logging, efficient checkpointing, and debugging tools, ensuring production-ready training. Moreover, TorchTitan incorporates innovative hardware, software co-design solution. So they have floated training and symmetric memory to maximize hardware utilization. And as a flexible experimental testbed, TorchTitan facilitates the curation and comparison of custom recipes for diverse training contexts. By leveraging TorchTitan, they developed optimized training recipes for the Llama 3.1 family and provide actionable guidance on selecting and combining distributed training techniques to maximize efficiency. All right. So they thoroughly assess TorchTitan from 8 billion to 405 billion and showcase its exceptional performance. By stacking training optimization, we demonstrate acceleration of 65.08% with 1D parallelism at 128 GPU scale, then more 12.59% more with 2D at 256 GPU scale, and then 30% more with 3D at 512 GPU scale. All right, so they're basically training different size models with different number of GPUs over the H100 optimized baseline. Got it. All right, so introduction, I don't think we need to know LLMs are doing this. Yep, everyone knows. LLM requires billions of parameters and training over trillions of tokens to get SOTA. Yeah, Llama 3.1, 4 or 5 billion, 15 trillion tokens. And yeah, so many GPUs, so many Rs. Similarly with Palm from Google, LLM training challenges are being tackled from all sides. So you need a delicate balance of parallelism, computing, and communication, all while navigating intricate memory and computation trade-offs. The massive resources required for training make it prone to GPU failures. Yeah, if you look at the Llama technical report, they also mentioned that they had so many GPU failures, but of course they had efficient restarts and stuff to quickly get back to training. And one thing that you need to do for this kind of stuff is to have periodic checkpointing. To optimize resource utilization and achieve elastic scalability, it is crucial to combine multiple parallelism techniques, including data parallel, tensor parallel, context parallel, and pipeline parallel. So, out of all of these, I am not super familiar with context parallel, but the others are fairly standard. By stacking these parallelisms with memory and computation optimization, such as activation recomputation, or you might know this as activation checkpointing, and mixed precision training and deep learning compilers, it is possible to maximize hardware aware utilization. All right. So, limitations of existing SOTA methods, non composable. So, it's difficult to stack different techniques. All right. Certain libraries do allow you to do that. So, I don't know what library they are referring to in particular, but I agree that if you're trying to do everything from scratch, then it's of course very hard. Inflexible and monolithic architecture, they are not modular to new techniques, optimization, hardware, and so on. Fair enough. A lot of things are super optimized for NVIDIA and then totally break on AMD. Inefficient hardware utilization, so you get suboptimal GPU efficiency. Fair. Insufficient support for production grade training. Got it. So they do not have things like failure recovery and model saving. Uh, is cumbersome, and then they don't have efficient distributed checkpointing, which is quite essential because you don't want your entire training run to be stalled because you need to checkpoint. That's like just purely wasted GPU's time. And then existing system falls short in harnessing the full potential of frameworks like PyTorch because okay, with new releases you have bug fixes, optimized kernels, new features, and compiler support, and they also have external dependencies. Yeah, so like for instance, NeoX, instead of using FSDP, which is PyTorch's implementation of stuff, they use DeepSpeed, which was basically the first uh, library to introduce it. And yeah, so root cause, lack of an expressive tensor abstraction. So the root cause of non-composability and inflexibility of distributed systems stems from the lack of using an expressive tensor and device abstraction upon which all of distributed parallelism, checkpointing, and efficiency optimizations can be built. All right, fair enough. If you don't have this, then you need to continuously, with every new thing, adapt your. Uh, okay, where's the highlighter? Yeah, with every new thing, you need to continuously uh, adapt your tensor and device management to, like, say when you start doing pipeline parallel or something, you need to then adapt based on that. Then the design principle is unified distributed tensor. So this, I guess they're using D-tensor here, and device abstraction. All right. So unified device abstraction represents the distributed system as a multi-dimensional array where each dimension corresponds to parallelism techniques, managing communication between devices and handling collective process groups. Yeah, communication between devices is, I guess, self-explanatory, and handling collective process groups is basically doing all reduces and these other nickel operations. A complementary tensor abstraction enables tensors to be sharded across this array, maintaining sharding specifications and supporting automatic sharding propagation. Together, these abstractions enable seamless composition. All right. So they basically assume that every dimension corresponds to one new parallelism technique. For instance, maybe one dimension is how do you shard your model layers uh, across different GPUs. Another layer is another dimension corresponds to the pipeline parallelism where you split the model into two, and then the inner dimension splits it further vertically. All right. So yeah, they're using PyTorch's distributed tensor D-tensor and the device mesh as the foundational components for TorchTitan. Through our work with D-tensor and device mesh, we identified key limitations and addressed them. I really like this because unless you're the PyTorch team does this very well. You need to actually build stuff using things you've put out. Otherwise, it just doesn't make sense for others to use it if you're not using it yourself. I hope, or I assume Meta is also using PyTorch for their actual Llama runs, but it would be great if Meta actually came out and released that code base as well. All right. So by using and extending D-Tensor, we developed TorchTitan, a production-ready system that enables composability, modularity, flexibility, and extensibility. TorchTitan facilitates the composition of 3D parallelism and so on. Okay, got it. To develop and evaluate, the core contributions are we advanced D-Tensor by extending its sharding to support ND parallelism, adding compatibility with Torch compile, and enabling efficient checkpointing of ND models via straight dict. And then we also resolve critical bugs. All right. We demonstrate how to compose and stack various parallelism techniques, facilitating exploration of multi-dimensional parallelism in LLMs. All right. Okay, what's up with this? Yeah. We enable novel hardware software co-design solutions, exploiting advanced hardware features to increase GPU efficiency, offer customizable activation checkpointing, and torch.compile. All right. We offer production grade training, Yeah, I really like this flight recorder thing, which allows you to debug crash stuck jobs and give you extensive logging metrics. We evaluate TorchTitan on the Llama 3.1 family with 1D, 2D, and 3D parallelism at a scale from 8 to 512 GPUs. And this is the result we were also reading in the abstract. Systematic training recipes, all right, and we show how modern and extensible architectures allow for seamless integration. Okay, yeah, now let's get into the core of the paper. Elasticity through composability. TorchTitan incorporates various parallelism techniques in a modular manner to enable easy, user-selectable combination of multidimensional parallelisms. This composability enables the tackling of difficult scaling challenges by enhancing the ease of frontier exploration. Okay. The codebase of TorchTitan is organized purposefully to enable composability and extensibility. We intentionally keep three main components separate and as orthogonal as possible. The model definition, which is parallelism agnostic, parallelism helpers, which apply data, tensor, and pipeline parallel, and a generalized training loop. Okay, this is really good because if any two of these are deeply integrated, you can't really do uh, the same thing for a new model. For instance, if you are integrating the model definition with the parallelism helpers, then all of a sudden, when you're introducing a new model, you now need to rewrite your parallelism helpers. If you're mixing a parallelism helper with a training loop, then all of a sudden, if you need a new parallelism thing, you need to rewrite your entire training loop. And if you want to use a subset, then you have to maintain different copies of the training loop and so on. And I hope you get the point. And all these components are configurable via TOML files with command line overrides and is okay, cool. Not a huge fan of TOML, but anyways, I that is not the most important thing here. Okay, so composable ND. We'll get to the figure when the paper refers to the figure. Okay, in composable ND parallelism training, in this section we will walk through the entire regime of scaling model training on large clusters, including meta-device initialization and core composable multi-dimensional pipeline parallelisms. To showcase how these techniques can be composed to train LLMs, the corresponding actual code snippets are in Appendix A. Okay, cool. Good that they've provided these snippets as well. Okay, so large-scale model initialization using meta-device. So given the exponential increase in model sizes, the first scaling issue appears even before the actual training starts. You need to instantiate a large model for sharding across the cluster, yet without overflowing CPU or GPU memory. Okay, so what this basically means is that before dividing the model, you at least need to know what the model is. And if the model is too big, it doesn't really fit on the CPU or the GPU. So you need to have some method of initialization which uh, you can use. Okay, so let's see. To tackle this, we enabled meta device initialization, where the model is first initialized on a meta device type. Okay, we'll see what is the meta device type. The meta device tensor only holds the metadata, not the actual data, making initialization ultra fast because you're not holding the weights or like even the randomly initialized weights. After that, we perform model sharding and transformation using the D-tensor, where each parameter holds a local shard that lives on the meta device. Let me reread this. We perform model sharding and transforming the model parameters into D-tensors. Okay, they first shard the model and then they transform the. So some parameters go on some devices and so on, and each parameter holds a local shard that lives on the meta device. Okay. Finally, we perform parameter initialization based on the user-defined initialization function, and then they use detensor to properly sync RNG. So basically, once every parameter knows which device or shard should I be on, only after that the initialization actually happens. This ensures that parameters start with the same value as if the whole model were initialized on one device. Okay, this is just ensuring your RNG is set properly because that's also non-trivial. Okay, now they're using FSTP. The original FSTP is an effective implementation of Zero and offers large model training capability. However, the original implementation, which is FSTP1, suffers from various limitations due to its flat tensor implementation. So at a very high level, they take all the parameters and create one big flat array. which is not ideal because there's no distinction between what's a model parameter and what's an optimizer parameter and so on, as far as I know. If I'm getting this wrong, please feel free to correct me in the comment section. And yeah, so for this, they created FSDP2. So given these limitations, TorchTitan integrates a new version of FSTP, which is FSTP2, which uses a per parameter detensor sharding representation and thus provides better composability with model parallelism and other features. Okay, so this core idea here is this. I really need to highlight properly this per parameter detensor sharding. So instead of having like one big flat tensor, now they're using this detensor approach. We'll see more about this, I guess, if we read the appendix. TorchTitan integrates and leverages FSTP2 as its default 1D parallelism, benefiting from the improved memory man. Okay, so you get a 7% lower per GPU requirement versus FSTP1 and a slight performance gain as well, which is quite cool. More details on FSTP2 and user examples are shown in Appendix B1. TorchTitan makes it simple to run when FSTP2 by embedding appropriate defaults, including auto sharding with your world size automatically. Nice. So for scaling to even larger world sizes, TorchTitan also integrates HSDP, which extends FSTP2 by creating sharding groups. You can look at that in Appendix B2. We'll do that. Okay. Now the tensor parallel thing. So TP and SP are key parallelism techniques to enable large model scale training. So TP is implemented in TorchTitan using the PyTorch row-wise and column-wise parallel APIs, where the model parameters are partitioned to D-tensors and perform sharded computation with it. With this, the TP implementation does not need to touch the model code, which allows faster enablement of different models. Okay, this is pretty cool. Yeah, I hope I can learn to highlight well. Similarly, now when you include sequence parallel as well, TP partitions the most computationally demanding aspects. SP performs sharded computation for the normalization or dropout layers on the sequence dimension, which otherwise generates large replicated activation tensor and thus can be challenging. And we can see more details in Appendix B3. Um, hmm. Okay, we'll probably go to Appendix in a bit. So this is pretty cool. Let me highlight this properly. I keep these highlights around because when I reread the paper, I know where's the most common or most important stuff. Because of the synergist relationship between TP and SP, TorchTitan natively bundles these two together, and they jointly are controlled by the TP degree setting. What's loss parallel? When the loss function is computed, the model's outputs are usually very large. Since the model outputs from TP or SP are sharded, on the huge vocabulary dimension, like if you have 120,000 vocabulary, you have 120,000 token long, 120,000 length tensor. So, but with TP and SP, these are pre-sharded. Natively computing the cross entropy requires gathering all the shards along the TP dimension, which incurs large memory usage because you need to bring it at least on one GPU to do this computation. With loss parallel, you can compute the cross entropy loss efficiently without gathering to every single GPU. This not only significantly reduces the memory consumption, but also improves training speed by reducing communication overhead. Okay, so you have again loss parallel by default. Okay, this is pretty nice. Let me also highlight this. Now we arrive at pipeline parallel, which is, I think, the most easy to understand parallelism technique. So for pre-training a large scale, Titan offers pipeline parallelism, which becomes essential due to having the lightest amount of communication overhead and leveraging P2P communications. So pipeline parallel views the model as a sequence of operations, chunking the operations and the parameters used by them into S stages, and which run on separate groups of devices. For instance, if we have 12 players and 4 devices, we'll put 3 layers on each device. Just an example, but I hope this puts the point across. In the typical case, one stage represents a single model layer or a group of n adjacent layers. But in theory, it could even be a partial layer. You could have just a attention or something happening on one device. For the forward pass, a stage receives input activations, except stage 0 where you have the tokens directly. They perform local computation and set output activations, sends output activations, except the last stage. Okay, the last stage performs a loss computation and begins the backward pass, sending gradients in the reverse. To improve efficiency, the batch input batch is broken into micro batches so that you do not have a lot of wasted GPU time. When you have these micro batches, you can keep feeding the GPU with micro batches. Okay, and you need to also overlap the pipelines, like the computation with the micro batch data, and this enables a variety of pipeline schedules with the schedules previously described in other works. Okay, so yeah, the training loop must account for creation of pipeline stages and executing a pipeline scheduler rather than working model.forward directly, because model.forward just tries to run stuff, but you, uh, one after the other, but you also need to account for things being on different GPUs and what should go where and so on. Because the schedule computes loss per microbatch, the loss computation, any logging code must be updated for PP, because to compute the batch loss, you need to somehow aggregate this. In TorchTitan, we propose to define a shared loss function to be used both by pipeline and non-pipeline code paths, and thus minimize divergence. Okay, nice. Interactions with data parallelism, such as ensuring the data parallel reduction happens only after the last microbatch in the schedule, and scheduling of shard and unshard operations when using 03 are handled transparently inside the pipeline schedule executor, simplifying the trainer implementation. Yeah. So if you're familiar with data parallel, you basically send different batches of data to different copies of the model so that you can run through more data at once. All right, so optimizing training efficiencies, navigating compute memory trade-offs using activation checkpointing. So activation checkpointing and selective activation checkpointing are standard training techniques to reduce GPU memory usage. So basically, you offload or you don't preserve some of your activation things to preserve GPU memory. But in contrast, when you need them again, you recompute them, making your pipeline a bit slower. It is often needed for after applying multidimensional parallelisms. All right. TorchTitan offers flexible AC and SSE options, utilizing torch.util.checkpoint applied at a transformer block level. The AC strategies include full AC, op level, and layer level. So op level, I assume, is you only offload selective, only recompute for selective operation. So within a transformer block, full AC works by recomputing all activation tensors. Op level saves results from compute-intensive PyTorch operation, only recomputes others. Layer level works in similar fashion as AC, but is applied to every X transformer block where X is specified by the user. Okay, sounds cool. So if the user just wants layer 10 to be handled differently for some reason, they can do that. All right, so regional compilation to explore torch.compile. So torch.compile, if you're not familiar with it, it was released with PyTorch 2, with Torch Dynamo as the front end to extract PyTorch operations into an FX graph, and Torch Inductor as backend to compile the FX graph into fused Triton code to improve performance. So at a very high level, what this means is that you're basically creating a graph out of your PyTorch operations. If you've used TensorFlow before, TensorFlow basically started off with this paradigm, and then they basically use the backend inductor, which is backend, which is torch inductor, which finds operations which are occurring together and tries to write efficient kernels for them, which can basically, if you have two operations and together they use 10 uh, internal steps. First, as an example, with the inductor, you might be able to combine both of them into one kernel, which only uses 7 steps, for instance. So you're saving 30% of steps. In TorchTitan, they use a regional compilation, which applies torch.compile to each individual transformer block. So instead, this has two main benefits. They get a full graph without graph breaks for each region, compatible with FSGP2 and tensor parallel, and more generally, torch tensor subclasses such as T-tensor and other PyTorch distributed training techniques. Since the Llama model stacks identical transformer block, torch.compile can identify the same structure being repeatedly compiled and only compiled once. Oh, nice. So instead of creating a graph of the entire model, you're getting a graph of just one layer and using that, since that same layer is being repeated multiple times, and this is for some reason more compatible with or better for these techniques. Torch.compile brings efficiency in both throughput and memory via fusions, and communication reordering in a model agnostic way. Before we further elaborate how Torch.compile composability helps TorchTitan uh, unlock hardware optimization performance gain with simple user interface with the integration of what's this sentence? I can't understand. Oh, it's not before, it's below. Okay. So asynchronous TP to maximally overlap communication. By default, tensor parallel incurs blocking communications before and after the sharded communications, because you're basically rematerializing the entire layer on every GPU, doing this and then uh, basically deleting everything from every layer, every GPU. Asynchronous TP achieves communication overlap by fractionalizing the TP matrix within the attention and feedforward modules into smaller chunks. So now overlapping communication collectives in between each section. So you might be doing the computation for chunk one, and at the same time you can perform the gathering of parameters for chunk 2. The overlap is achieved by a micro pipelining optimization where results are being communicated at the same time that other chunks of the matmul are being computed. PyTorch async TP is based on symmetric memory abstraction, which creates intra-node buffers to write faster communication collectives. This is done by allocating a shared memory buffer on each GPU in order to provide direct peer-to-peer access. Sorry. With TorchTitan's integration of Torch Compile, async TP can be easily configured in TorchTitan to achieve meaningful end-to-end speeds on newer hardware, H100s or newer GPUs with NV switch within node. Okay, this is quite interesting. I wasn't super familiar with async TP, but it looks quite interesting and we can read more about it. Boosting throughput with mixed precision training and float rate support. Mixed precision training provides both memory and computational savings while ensuring training stability. So the idea here is to use low precision operations for some stuff and high precision for others. FSGP2 has built-in support for mixed precision training with TorchTitan that covers the popular uses of FSGP all gather and computation in bfloat 16, and lossless FSGP reduced scatter for gradient in high precision like float 32. TorchTitan also supports more advanced mixed precision training with Float 8, a derived data type on newer hardware. The Float 8 features from Torch AO Float 8 supports multiple per tensor scaling strategies, including dynamic, delayed, and static, while being composable with other key PyTorch native systems such as Autograd, Torch Compile, FSGP2, and TP, with Float 8 all gather compatibility. All right. So this is basically on how to do mixed precision training, and they also support Float 8, which is becoming quite popular. And do note, Float 8 is a derived data type, so it's not a, I don't know what they call. So Float 32 and other these other data types have like direct definitions in the PyTorch code, while Float 8 and stuff are based on top of them, and so they are derived data types. So now production ready training, you need distributed checkpointing and debugging. For distributed checkpointing, uh, okay, they facilitate model reuse in application like inference and evaluation, and they also provide a recovery mechanism for failures. An optimal checkpointing workflow should ensure ease of reuse across different parallelisms and maintain high performance without slowing down training. So there are two typical checkpointing methods. The first aggregates the state into an unsharded version that is parallelism agnostic, facilitating easy reuse but requires expensive communication, because every time you want to save a checkpoint, you need to first send everything to at least one GPU. The second method has each trainer save its local shard, which speeds up process but complicates reuse due to embedded parallelism information. What this basically means is that, so if you have 128 GPUs and you have parallelism set up in one way, you that might be then your shards will be saved in a different way as compared to if you have 256 GPUs with a different parallelism organization. Okay, so DCP addresses these challenges using DTensor, which encapsulates both global and local tensor information independently of parallelism. What DCP does is it converts this information into an internal format for storage. So during loading, DCP matches the stored shards with the current DTensor based model parameters and optimizes it, fetching the necessary shard from storage. TorchTitan, which utilizes all native PyTorch parallelism, effectively uses DCP to maintain balance, efficiency, and usability. Furthermore, DCP enhances efficiency through async checkpointing by processing storage persistence in a separate thread, allowing this operation to overlap. TorchTitan utilizes DCP's async checkpointing to reduce the communication overhead by 5 to 15 times, which is quite good. So what they're basically saying is that even if your new GPU topology might not match the topology from the checkpoint, because DTensor base has DTensor keeps information about the global and local tensor information independently of what parallelism is being applied. You can use the DTensor metadata to sort of rebuild a model. Okay, and now flight recorder. A common failure mode when developing parallelism code or when running at large scale is to observe a nickel collective timeout, which is basically things like all reduce communicating between GPUs, and then they need to figure out the root cause. Since communication kernels are typically async from the perspective of the CPU, by the time something times out, it can be very hard to pinpoint which operation failed and why. The flight recorder for nickel collectives helps resolve this. It records the start time and end time as well as the NQ time. So NQ is on the CPU when did it send the operation, and start and end is on the GPU for every collective. Additionally, it logs metadata such as which process group was used, who the source rank is, and destination, tensor size, and stack traces. They find that the data contained in the flight recorder helps debug collective hangs and P2P hangs caused by bugs in parallelism code. For PP, there might be schedule bugs due to missing or improperly ordered sender receive. Analysis based on flight recorder can pinpoint the latest sender receive that has completed. For FSTP or TP, it is possible to determine whether one or more hangs have has not called into a collective, perhaps due to a bug in PP scheduling or faulty logic in TP. Okay, so I really want this to be integrated in other things like LitGPT and NeoX because this seems really cool. All right, now with experimentation, now let's dive into the results. So the training Llama 3.1, 8B, 70B, and 405B from 1D to 3D parallelism, from 8 to 5 went to GPU. So some of them will outright not work. For instance, 405B in full precision does not fit on 8 GPUs. A walkthrough of the code base is an appendix. Okay, so they have H100s with 95 GB memory. What's the note? The H100s use are non-standard. They have HBM2E and are limited to a lower TDP. The actual peak flop should be between XSM and NVL, and we don't know the exact value. Okay, for some reason they got weird H100s. Okay, two hosts form each host is equipped with 8 GPUs and NV switch. Okay, two hosts form a rack connected to a torch switch. A backend RDMA network connects the torch switches. In TorchTitan, we integrate the checkpointable data loader and provide built-in support for C4 dataset, the English variant, a colossal cleaned version of Common Crawl Web Corpus, and they use this for experiments. And they use the official one TikTok in released with Llama 3.1 as the tokenizer. Okay. So performance to showcase the elasticity, they train different GPU size, different GPU counts and different model sizes. To demonstrate the effectiveness, we show how training improvement throughput improves. Got it. We note throughout our experimentation, model memory readings are stable, whereas throughput numbers are calculated and logged every 10 iterations and are always read at the arbitrarily determined 98 iteration. Okay, so every 90 iterations they read this. We do not report model flop utilization MFU, which is becoming quite popular. Let's see why they don't report it. Because when float 8 is enabled, both bfloat 16 tensor core and FP8 tensor core are involved, but they have different peak flops. And the definition of MFU is not well defined under such a scenario. Okay, because you're going to compute your MFU based on what's the peak flops, and when you're using two different kernels, sorry, tensor cores, you don't know what's the peak flop. We know that 1D Llama 3.1 8B training on 8 or 120 H100 GPU without floated achieves 33% to 42% MFU. Okay, sounds good. 1D parallelism, Llama 3.1, 8 GPUs, mixed precision, selective activation checkpointing, a local batch size of 2 and global batch size of 16. Local batch size means how many things per GPU, and global batch size of 16 means since you have 8 GPUs, you have 8 into 16. So with FSGP only you get 6,258 tokens per second, and 81.9 gigabytes of memory. Then you add torch compile, your memory usage drops and your throughput increases. So you get a 6.64% improvement. And then you add floatate as well, and then it becomes a 50.35% improvement. Okay, this is quite cool. Now let's look at a 128 GPU scenario. You can see that uh, the batch size remains the same with FSGP. The throughput is a bit lower, and you're using 67 gigabytes of VRAM. But once you're in going with all optimizations, you have a pretty comparable throughput. Like it's only 90 tokens per second less than 8 GPUs, even though you've essentially done 16x GPU increment. Now we have 2D parallelism where we have FSTP and tensor parallel. You also have torch compile and floatate with 256 GPUs. So now basically you have mixed precision training, full activation checkpointing, FSTP degree of 32, TP degree of 8, local batch size of 16, and global batch size of 512. Basically, this means that with this FSTP degree of 32, you have 32 GPUs running data parallel. So you basically have 30, how am I computing this? Since you have 512 global batch size and 16 local batch size, so it means you have 32 different uh, local batches going at the same time. So you have 32 way data parallel here, and also they give you a TP degree of 8. So every parameter is sharded across 8 different things, and of course 32 into 8 is 256. So you can basically compute that. So with plain 2D, your throughput is 897 tokens per second. As soon as you add async TP, you're doing better computation and communication overlap. You get a throughput of 12. You get an increase of 12.59%. Okay, so these are the two things they're comparing here. Now let's look at 3D. We have FSTP, TP, and PP. Okay, this just sounds a bit weird to read out, but yeah. You okay, and remember they also had floatate and torch compile here. Here you have also async TP. Now you have a 405B model. This was a 70B model. I really want one table or one good visualization where you have 8B on, say, all GPUs, and I can look at the graphs. This is a just bit hard to pass, but okay. So you have the Llama 3.1 405 model. I should also highlight this because in the future I might think, why is this so different? 512 GPUs, mixed precision, full activation checkpointing, FSGP degree 4, TP degree 8, PP degree 16, because of course you can't fit everything on with pipeline 405B on one node. Local batch size 32, global batch size 128. So basically, FSGP degree 4 is how many data parallel ranks you have. TP degree 8 is how many 10 GPUs, each parameter is sharded across, each layer or thing is sharded across how many GPUs, and pipeline parallelism degree of 16 is how many times is the model split vertically. So you have 16 splits of the model. Okay, and you have the schedule. So 1F, 1B is one forward and one backward. You get 100 tokens per second. You can also do interleaved, where you uh, interleave the forward and backward, you get a 30% improvement. Quite nice. Now, scaling with TorchTitan 3D parallelism. The LLM scaling law imposes challenges due to increasingly large model size and huge amount of data. It requires applying parallelism strategies on massive number of GPUs. TorchTitan provides the ability to compose different parallelism to effectively scale model training. This section discusses observation and motivation. To apply TorchTitan 3D when training LLMs at scale, please note that there could be many 3D combinations, but we choose to discuss one combination, which is okay. So if you have 2 to 512 GPUs, you should use 1D FSTP. So it's easy to apply a communication computation overlap. So 1D parallel, basically you have one model copy per GPU, and then each model copy sees different batches of data, and then you just aggregate the loss before doing a backward. Large model exposed communication. Now you have 2D parallelism where you have TP plus FSGP. This is when you have 512 to 4192 GPU, and if you have even larger model, you use all three combined. Model further split by layers, small communication bubble decided by a schedule. Max TP degree they recommend here is it. Okay, interesting. Now scaling with FSDP. FSDP is generalized technique which can be applied to any model arc, making it a good choice for first or the only degree of parallelism, as long as FSDP communication faster than corresponding computation, which in case of LLMs trained up to 100 or in say 512 GPUs, and there is no need to reduce effective per batch size to be below 1 for reasons mentioned in the TP section. 1D FSDP should be sufficient. Now you have ring-based nickel collectives all gather in reduced strata, which incur a latency overhead when becoming severe at large scale. FSDP alone will become less efficient due to collective latency increasing linearly with the vault size, because you, of course, need to communicate between each and every GPU, resulting in FSDP collectives that cannot be hidden by the computation anymore. To further scale out, one needs to consider combining model parallelism solutions such as TP or PP. Okay, now 2D, they're using tensor parallel. Model parallelism tensor or pipeline can help avoid the increased collective latency faced by scaling FSDP alone. TP can further lower the effective local batch size to a minimum of 1 over TP degree when the local batch size is set to 1. As TP sharded models on multiple GPUs work jointly to process the same batch, this can be vital for reducing peak memory usage, because you'll basically have the same model seeing the same batch of data, but that model is now split say across 4 GPUs. So each GPU does not have the effectively each GPU has less overhead, like less uh, base memory usage, and then when new data comes in, it only needs to rematerialize one layer onto that each GPU, do the forward, scatter, remove the layer components which were not already present on it, and keep doing this. Okay. In addition, TP performs feature dimension sharding that can bring more optimized matrix multiplication. Okay, so this is just optimizing for how to do your matmults. TP introduces extra blocking collectives. In practice, TP is only applied within a node that have fast interconnect. Async TP could improve the performance by fully overlapping the communication, but could not scale to multi-node easily. So the TP degree is usually limited to it, because doing async TP across multiple nodes is not scalable. This means to scale beyond an ultra large number of GPUs, we need 3D parallelism. And with 3D parallelism, you're applying pipeline with 2D. Compared to other model parallelism, pipeline parallel requires less communication bandwidth by virtue of only transmitting activation gradient between stages. It is especially useful to further reduce FSTP communication latency when the FSTP vault size becomes large again. That FSTP plus TP still exposes FSTP collectives, or to train bandwidth limited cluster. Let me reread this. Pipeline parallel requires less communication bandwidth by virtue of only transmitting activation gradient between stages. Yeah, because you're once one vertical shard of the model ends, you only need to communicate the activation to the next shard, and during backward only communicate the gradients. We note that the performance of pipeline parallel, in particular the bubble size, could vary by pipeline schedules being used and the micro batch size, assuming fixed global batch size and the world size. Yeah, if you're not doing your scheduling well, you basically have lots of spare time. You should read the pipeline parallel paper. There is this one famous figure also, which is used in a lot of blog posts to communicate this. Now demonstrating adaptability. Ongoing work, they're trying to do 4D parallelism and zero bubble pipeline schedules. So incorporating context parallel, which would mean you now have 4D parallelism, and leveraging distributed pipelining package to support zero bubble schedules. If you're not familiar with this, this used to be called PP in the PyTorch ecosystem, but now it's a part of Torch distributed pipelining API. This demonstrates TorchTitan ability to evolve, and TorchTitan flexible architecture also empowers users to easily integrate by providing a model and efficient testbed. TorchTitan enables users to rapidly benchmark new techniques. This has led to refinement of new production grade data loader, improvement to zero implementation, advancements in Atom-based optimization, and training on of a top-tier diffusion model. Okay, really nice. Now let's look at the related works. You have Megatron, DeepSpeed, PyTorch distributed offer APIs. Nemo built on top of Megatron LM offers a package solution. PyTorch native solution like TorchTune focus on fine tuning. Surprisingly, do not talk about Neonix. TorchTitan differs from these solutions by focusing on production grade pre-training using PyTorch native APIs, libraries extra designed with elastic composability and so on. Okay, the conclusion is that it's a powerful framework. You can do all of this stuff, highly flexible, blah blah blah. Okay, I we see the point here. Let's jump to the appendix and acknowledgements. Okay, I recognize some of them here because they are quite popular in the PyTorch ecosystem. I believe Sumit is the head of PyTorch, or I don't know his exact role title, but he's the guy who introduced or like gave the leading talk for PyTorch 2.0. Let's go to the appendix now. A composable 3D parallelism walkthrough. Okay, the first step is to create an instance on the meta device. We then apply PP by splitting the model into PP stages according to pipeline parallel split points config. Note that PP with loop schedules we may obtain multiple model parts from PP splitting where each item in model parts is one stage chunk. Next, we apply single process multiple data style distributed training techniques including TP, activation checkpointing, so on for each model part before actually initializing. Okay, so you basically do every possible split a priori because with the device detensor abstraction you have a lot of these and sorry with the meta device thing you can do this, and only once you split everything then you initialize it. So let's see, with this meta context manager you're initializing the model, then you're applying the pipeline schedule, and then you're doing all your parallelization. Only then are you moving it to the GPU and initializing the weights. To apply PP to the model, we run the following code at the high level. Pipeline llama manual split splits the model into multiple stages according to manually given config by removing the unused model components from a complete model. Then they build a pipeline schedule from torch.distributed.pipelining. There you have 1F1B, gpipe, and interleaved 1F1B. Okay, so this is your thing. Now with TP and FSGP, they are both the SPMD style parallelization. To apply TP, we utilize the D-tensor parallelize module API by providing a TP plan, which tells how to do the tensor parallel. Let's see. So for every layer ID and transformer block, you have a plan where you have attention norm should be sequence parallel, attention should be, okay, this should be your model input prep step, and then you have basically do the parallelization. Finally, we apply the FSGP2 by wrapping each individual transformer block and then the whole model. Note that FSGP2 implementation in PyTorch comes with mixed precision training support by default, which is quite nice. By default, we use torch.bfloat16 on parameter all gather and activation computations and use torch32 on gradient reduce scatter. You might be wondering why this, because Empirically, people have noticed that if you have low precision gradients, it becomes unstable or it doesn't converge as well. So let's see. Uh, this is an optimization. Do not reshard after forward for the last block since FSDP would prefetch it immediately. Okay, reshard after forward is true or false based on this thing, and then you're basically doing your sharding. Okay, supplementary material. So FSDP two improvement over the FSDP1 flat parameter grouping, specifically parameters now represented as D-tensors. This provides better composability, of course, and manipulation of individual parameters, allowing sharded dict to be represented by D-tensor without any communication, provide for simpler initialization. As a part of the rewrite, FSGP2 implements an improved memory management thing by avoiding the use of a record stream. Mhm. This enables deterministic memory release, and this leads to lower GPU usage. For instance, you can see 7% lower GPU memory usage with FSGP2. In addition, by writing efficient kernels, it's on par performance with FSGP1 and even an average gain of 1.5%. Nice. The performance gains are a result of employing two small performance improvement. First, only a single division kernels run for the FP32 reduced scatter. So pre-dividing the local FP32 reduced scatter gradient by volt size instead of a two-step pre and post divide. Secondly, in TorchTitan, FSGP2 is integrated with a default of not sharding the final block in a transformer layer during the forward pass, since it will be immediately regathered at the start of the backward pass. Thus, we can skip a round of communication delay. So this is like uh, optimization, which you just notice that since this is obviously going to happen, why should I waste my time doing the regathering, uh, like not sharding the final block because it will be immediately regathered. All right, usage. This is fully integrated FSGP2 with TOML files. Okay, HSDP, which is hybrid shard data parallel, which supports larger world sizes. In FSTP, all devices are part of a single global group. However, at some point, adding more computation offset by increasing communication. So, because you have latency of sending everything to every other GPU, at this saturation point, FSGP throughput will effectively flatline, even if you add more GPUs. HSDP obviates this to some degree by creating smaller sharding groups within the original global group where each sharding group runs FSTP within it, and gradients are synced across sharding groups at set frequency during backward pass, so that global gradient is maintained. This ensures speedy communication and so on. By using sharding groups, we have seen FSTP can extend the world size by 3 to 6x. This, of course, depends on your interconnects as well. TorchTitan makes it easy to run HSTP with two user configurable settings for sharding group size and replication group size. HSDP is enabled in TorchTitan by modifying the previously mentioned knob. This is effectively the GPU count that will run FSTP sharding among its corresponding group members. From there, we must spec this with which controls how many sharding groups we are creating. The product of both replicate and shard degree must add up to total world size. Alright, that makes sense. Enable example on a 128 GPU cluster, you may find that sharding over 16 GPUs would be enough. Therefore, you would set the data parallel size to be 16. The data parallel shard degree to be 16 and the data parallel replicate degree to be 8. So you have 8 groups of 16 GPUs to fill out. Now with tensor parallel, it partitions the attention and MLP modules. This allows for multiple GPUs to cooperatively process a single transformer layer, and that would otherwise exceed a single GPU's ability. And this adds some already used altogether and reduce scatter operations to synchronize the intermediates. Due to additional collectives, it needs to happen on fast network like NVLink. When training LLMs, TP is usually combined with FSGP, where TP shards within nodes and FSGP shards across nodes. Because of the synergistic relationship between TP and SP, TorchTitan natively bundles these two together and they are jointly controlled by TP degree setting. Setting this to 2, for example, would mean that two GPUs within the node will share the communication load for each transformer layer attention and MLP module, and normalization dropout via sequence parallel. Loss parallel is implemented by a context manager as it needs to control the loss computation outside of the model's forward, because once the forward ends only then you do the loss. It can be enabled via enable loss parallel. Okay, this is interesting. With pipeline parallel, we expose several parameters to configure PP. Controlling pipeline parallel degree controls the number of ranks. Pipeline parallel split points accepts a list of strings representing layers fully qualified name before which a split needs to be will be performed. Thus, the total number of pipeline stages V will be determined by the length of the list. Pipeline parallel schedule accepts the name of the schedule to be used. If the schedule is multi-stage, there should be V greater than one stages assigned to each pipeline rank. Otherwise, V equal one. Uh, Pipeline. I did not realize I'm running out of battery. Okay, I guess I'm towards the end of the paper as well. Pipeline parallel micro batches control the number of micro batches to split a data batch into. Activation checkpointing, we discussed this earlier as well. You selectively checkpoint per layer or per operation. You are basically of doing some recomputation to gain some GPU memory, like offload some GPU memory. So it's enabled via a two-line setting. Especially mode can be non-selective or full. With selective, you need to tell selective AC type, which can be either a positive integer to select selective layer or OP to enable selective operation. Per layer takes an integer input to guide the checkpointing policy, where one equal checkpoint every layer, two every other layer, three every third layer, and so on. Per operation is driven by the save list policy, with which flags high arithmetic intensity operations such as matmul and as the dot product attention for saving the intermediate results. Note that for balancing total throughput, only every other matmul is flagged for saving. With async TP, the symmetric memory collectives used in async TP are faster than standard nickel collectives and operate by having each GPU allocate an identical memory buffer. Symmetric memory relies on having NV switch within each node. Async TP is enabled within the experimental section and turned on or off via this. Okay. With FSTP2 mixed precision in TorchTitan, mixed precision is controlled by the multi mixed precision policy, which is then customized via with param D type and reduced D type. The reduced tree type in FP32 means that reduced scatter in the backward pass for gradient computation will take place in FP32. All right, so this is a really good paper. I think I missed some figures, so I'll quickly go over them. Tensor parallel in detail. So basically, if you have say a 5 by 16 GPU, what you're going to do is your weights are sharded alternatively. So the first thing is sharded column wise. So you get some outputs. So instead of getting the entire output, you get a 5 by 2 output instead of a 5 by 4 activation output. And then the next shard is done row wise, because if you can't operate on this column wise, like you'll have to have a synchronization point before this if you want to do a column wise matrix multiplication here again. So yeah, this is very well explained in the zero paper. It's not very well explained in the zero paper, but this is something I know from the zero paper. And then you do this mid-mal, you get 5 by 12 things. And with the all reduce, you can basically do some kind of averaging to get your final outputs. With FSTP2 tensor parallel sharding layout. So this was just tensor parallel. Here you basically have, you can see you have column wise sharding with 2D and row wise weight sharding. You have you have how many GPUs? I believe you have 8 GPUs here. So the first matmul is via okay. So I guess the point here is that you're doing splits in two ways. Across this you have across this blue thing you have column wise sharding. So every column goes on one GPU, and across this blue thing you have row wise sharding. So every row goes to one new thing. But as you see, you have TP of degree 4. That is why you have four different things. After the computation, you need to have all gather and reduce scatter. But what I don't understand is, what does this green here symbolize? FSTP2 plus tensor parallel TP degree 4. TP degree 4 is this with two, oh, so there's two nodes, right? So each node, one node has GPU 0, 1, 2, 3, the other node has 4, 5, 6, 7. So GPU 0 is basically connected, going to interact more with GPU 4, and across nodes also you're doing this kind of, basically you're doing the same operation across both nodes. So each node has basically one data parallel thing running. Uh, so I believe, yeah, if I realize I made a mistake, I'll probably add a comment about this. And I think I also did not do this. Okay, the init you have a config, you initialize the model. Then if it's float rate, you do the float rate swapping. Then if it's pipeline parallelism, then you choose this. If it's TPSP, then you do that. Checkpointing, compile, and FST. All right. I think overall it's a great paper too. If you're already familiar with things, to just understand it. And I also wanted to become more familiar with the TorchTitan framework. So yeah, thank you guys for joining in. If you have any suggestions, feel free to let me know in the comments. See you again next time.